Okay, this kind of question really is what you're expecting in the exam. Really important that you grasp what the diagram's showing by using the words. So we have a pole AB. So the object we're going to draw forces on is this pole. It's a uniform pole. We've got the length, which is marked on the diagram. We've got the wall is rough, okay, and vertical. The string, of course, is light and inextensible, and it runs from B to D, where it's attached to the wall. We've got a particle of weight 2W attached to the pole at C. So there's a particle here. Okay, the pole is in equilibrium, it always will be, in a vertical plane, blah, 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 blah. The string is inclined at the angle theta, and as often they tell us, sine of theta. Okay, and it's modeled as a uniform rod. So, okay, at this stage, you can put all the forces on the force diagram, and you can set up your three equations. And since we have a rough point of contact, you can set up the friction equation. So, consider forces on the rod. It's a uniform rod, so its weight is going to act at the center. So we have, we could call it W. Yes, it wants us to call it W. The length is A, so because it acts at the center, this distance is A, so is the distance on the other side. Okay, so that's the weight. Anything else that exerts a force on the rod has to be something touching it. So the string is touching the rod at this end, and the tension in the string must act along the string. The wall is touching it here. Now the wall can exert a contact force, so there's a normal component of that contact force called the normal reaction, but it's a rough wall. So we're also going to have a parallel component, so we have to think which way would it slip. Well, probably if that was a totally smooth wall, it would slip downwards, wouldn't it? So I'm going to guess that friction is pointing upwards, but don't agonize too much. If you make the wrong guess about the direction of friction, it'll probably just turn out being negative when you set up your equations. So the wall's touching it, the string's touching it, and there's this particle at C which is touching it, and the weight of that particle is 2W. So I've got a downward force 2W. All right, and this force diagram is now getting a bit cluttered. It will make it's by no means a bad idea to draw your own copy. And I've done that here. And I might as well do my trig processing. So they've given me sine of theta is 3/5, which tells me the ratio opposite over hypotenuse is 3/5. Oh, look, it's a 3, 4, 5 triangle. So cos of theta is 4/5, and tan of theta's that will be 3/4 if I need it, which I probably won't. Okay, right, now to the serious business. All right, if this is set up correctly, then I've got some chance of earning marks from my equations. So we're going to do three things. We're going to take moments. Oh, I should have the names of these places. This is A, this place here is called B, and this end, no, it's not, it's called C, and this end of the rod is called B. Okay, so I'm going to take moments about a point, and I'm going to do my resolving horizontally and vertically. And really, just as long as you churn out these three equations, you should be fine. But if you're taking this approach, then you're going to say A plus B plus C. We're not going to necessarily churn out simply the equations we need for part A first. So we want to get credit for all of them. So exam technique says announce we're doing all the parts. So we can say the resultant force is MA. So we've got 1, 2, 3, 4, 5 forces. I like to do this with vectors, so I do horizontal and vertical at once. But if you prefer to do your horizontal and vertical equations separately, my top line will be your horizontal equation. I should show my x and y directions really. Okay, your top line will be the horizontal equation and your bottom line will be the vertical equation. On this side we need ma, where a is the acceleration, but whenever that's equilibrium, the acceleration will be 0, 0, and multiplying it by m won't make any difference, so just 0, 0 will do here. So I've got F, which is a vertical force acting downwards, 0 minus F. I've got R, which is a horizontal force in the positive x direction. I've got W, which is a vertical force. So F was acting upwards, wasn't it? I've got W, which is a vertical force in the negative direction. I've got 2W as another vertical force in the negative direction. And then I've got this force, which I should call T, because it's a tension in the string. And this is the one that needs resolving. It's acting on angle theta. So I'm going to have a T and a T for the magnitude. There's going to be a theta and a theta. I've got to get the sine and the cos the right way around. Well, I can see that the theta cuddles up to the x direction. So the x bit is going to get the cos theta. The y bit is going to get the sine theta. I can see it's acting in the negative x direction, but the positive y direction. So I've got a horizontal and a vertical equation. If you like writing them out separately, this is what they look like. But whether you write them in vector form or as two separate equations, you should by now have earned 4 marks. Okay, method mark for each equation and an accuracy mark for having it spot on. Okay, to get your method mark, all the forces that should be included must be included. No extra forces are allowed to be included. Anything that should be resolved must be resolved with a cos theta or a sine theta. Anything that should not be resolved must not be resolved. So basically the only errors you're allowed is to have sine and cos the wrong way round, or to have maybe the odd sine error. Okay, so we have our first 2 equations. Our third equation is going to be moments equation. So you always think, where would the smart place be to take moments? Well, we look for unknown forces that we'd prefer not to have to deal with. And I think there are clearly 2 unknown forces at A, so taking moments about A might be good. The other candidate might be B, okay, because R doesn't have a moment about B, because it acts through B, and T would be eliminated, but I think the obvious choice is A. So let's take clockwise moments about A. So the point of that is that the forces F and R that act through A do not have to be included in my moments equation. So I've got clockwise forces, so think holding A steady. If I pull down with a W or a 2W, I'll get clockwise ones. So I'm going to have a plus W times the distance of W is going to be this one which I've marked A. So plus W times A, plus the 2W is also tending to act clockwise. The distance for that one I'm going to have to work out. So the overall length of the rod was 2A, but this bit at the end is x, so it's actually going to be 2A minus x. And then the final force is this T. Okay, now whereas the W and the 2W were already perpendicular, I didn't need to resolve those. T, I'm going to need the perpendicular component of T, in other words, the component in the y direction, which I've already got here. It's T sine theta. So I'm going to have minus T sine theta, because I can see that if I held A fixed, this T would tend to rotate it anti-clockwise, and I need to multiply that perpendicular component of T by the distance, which is the full length of the rod, 2A. And because it's in equilibrium, the total of the moments must equal 0. So now I've got 2, 4, 6 marks for 3 correct equations, and I might even get a mark for using my theory of friction. So if it's about to slip, okay, I don't know if it is or not yet, but I expect I'll be considering this case. So I can always talk about if it's about to slip, and if it is, then F equals F max equals mu times the normal reaction force. So I've got that ready just in case I need it. So no idea which order I'll use these things and whether I'll use them or not, but because I've put A, B and C here, any of these that are useful for any of the parts I should get credit for. So now I need to look at what I was asked to find. So I was actually asked to find the tension first. Okay, so I'm very glad I left that in my moments equation. So I'm going to look at the equations where tension appears. Well, it appears in everything. But this equation here, this horizontal one, I won't be able to find tension until I know the normal reaction force, or this one I'd need to know friction. Whereas from this one here, okay, I will just need to know x and w and a, but all of those things are in the formula, so it looks like I'm just going to be rearranging my moments equation to do part A. So rearranging A, this term here, this T sine theta times 2A, I'm going to add that to both sides, make it the subject. And sine theta, I know, is 3/5. So T sine theta times 2A equals these two terms. So I'm going to multiply out the bracket, WA plus 4WA, and then 2W times minus x gives me minus 2WX. So there's a common factor of W in this. So I may as well combine these two terms and take out that common factor of W right away. Okay, now I want T on its own, so I'm going to need to, I've got 3 times 2A is 6A, so I'm going to divide by that, and I'm going to multiply by 5. So I'm going to have 5 over 6A times what I already had over here, which was W brackets 5A 5a minus 2x, and I'm going to compare that with what the question told me to aim for. Well, it wants a 5 and over a 6a and a w and a 5a minus 2x. In fact, that's exactly what I've got written here, except with the w at the end and everything else combined into one fraction. So my 5 is here, my w is there, my bracket is there, and my 6a is there. So I can write as required, I've got there convincingly. Okay, onwards to part B. Okay, in part B I'm given more information. I'm now given the vertical component of the reaction force is 7 over 6w. So, terminology really important here. The reaction force that they're referring to, they don't mean the normal reaction force, so that's not vertical. They're saying the vertical component, this contact force that's split into the normal reaction and the friction, these two forces taken together are called the reaction force. So this friction force here can be referred to as the vertical component of the reaction force. So they're actually telling me in code that F equals 7 over 6W. All right? So watch out for that use of reaction force to mean R and F combined. Okay? So knowing what F is, the bottom line here, which I've written out as the vertical equation, I can now sub in my 7 over 6W here into this equation. Okay? It tells me to find x in terms of a, so I'm not allowed to leave t in it. So there's a t in this equation. Oh, but look, I've got t here in terms of stuff that I am allowed to use. So here are the three pieces of information that I've got to put together. So I'm going to sub into this equation. F I now know is 7 over 6w, minus another 3w, and then plus t, which is this big expression here. And I've got to multiply that by sine of 3 theta, which we found before was 3/5. So that 5 is going to cancel that 5, and this all equals 0. So I think I feel like multiplying this up by 6a. Oh, and every term's got a w in it, so I can divide through by w. So multiplying this by 6a, the 6 disappears, I get an a. Multiply by 6a, and this term here, the 6a, is going to disappear from the bottom. So I think I'm doing well. I need to just multiply out these brackets. I've already got minus 11a here. 5a times 3 is going to be plus 15a. Minus 6x equals 0. So 6x on this side, and I've got minus 11a plus 15a is plus 4a. So x is going to equal 4a over 6, which cancels down to 2/3 a. And that is, okay, so I should flag this up. This is my answer to B. So the answers are coming in the order of the question, but they don't have to. And then the last part of the question is to find the horizontal component. It's going to be in terms of W of the reaction force exerted by the wall on the pole. So again, they're talking about a component of the reaction force. The F and R together, their resultant would be what they're referring to as the reaction force. So here they're asking for the horizontal bit, which is just R. So I have to go back to the equation that had R in it. And here it is. It's the x row of the vector equation, which I've summarized here. Very simple one. R minus t cos theta equals 0. Okay, so R is what I want to find. So let's make that the subject of the formula. R equals, it's going to be t cos theta. Well, look, there's my t. When I substitute that in, here's my t. My cos of theta is 4/5. We worked that out before. And look, the x in this formula, I now know that x is 2/3 a, so I can substitute that in as well. So I've already cancelled the 5 on the bottom of cos theta and the 5 here. I can cancel this 4, well, down to a 2, and the 6a on the bottom becomes a 3. I'm going to have a w on the top, and then the 5a minus 2x is going to become 5a minus 2 lots of x is going to be minus 4/3 of a. And because this bracket, 4/3, that's a 3 on the bottom. Okay, because this bracket has a common factor of a, and there's an a on the bottom, I can cancel a's as well. 5 minus 4/3, well, 5 is 15/3, so this is 11/3 w times 2 all over 3, so this is going to become 22w over 9 equals R, and that is my final answer.